Okay, so let us start. This course is in English apparently. So we're going to study Introduction to Electrodynamics, and I'm happy to see all of you here. I know some of you didn't sleep so well, same for myself. I know the situation is not so great, and I hope peace will come soon and we can relax a bit more. If there'll be an alarm, we'll go downstairs. And maybe someone should be responsible to know whether the people that are watching us now, how long does it take them to come back in case of an alarm. If there will be only one or two people which have an alarm, we will continue the lesson. But if a majority over there will leave for an alarm, then we'll stop the class here. So maybe someone will tell me what to do based on some reasonable point of view. We're not going to define it exactly, but this is going to go happen. This one.
כן, רק ללחוץ שם על המיקרופון, שאני אראה.
ביד ידני?
לא עם העכבר.
Okay, so I just mentioned those people at home that the course is in English, and in case of an alarm, we'll have to leave this room and hopefully they'll be quiet. So let us start. The course is Electrodynamics, and the essential book is going to be Griffiths, but during the class I'll give you other names of other books, and of course you can use chat and things like that to further expand on the book. So the goal of this course would be, from my point of view, divided into several goals. One of them is that you take this book in English and you read it and you understand it. We're going to start actually in chapter 2. Chapter 1 is a mathematical introduction, so you should read chapter 1 by yourself. Chapter 2 you should also read by yourself. And I'm going to discuss it a little bit from my point of view, my angles. I'm going to point out what I believe are the difficult problems in the book, or things that you can expand a little bit, or some different point of view or something like that. But essentially most of the material is given in this book, and the idea of reading is very simple because you are in the third year. So essentially now when you finish third year, more or less, in the future there's no more books, so you should be able to read a book or use chat and a book and then be independent. So this is your chance. This is the way I see one of the main goals of this course. I highly recommend it. At least you'll learn English, maybe also physics. And Griffiths, in my opinion, is a very good book. He's very, he knows how to give the material. This course is more or less divided into two. The first part of the course, you had similar things in other places. So we are going to just go sometimes a bit deeper or have a more physical perspective. For example, in course mathematical physics, you studied Laplace equation, for example. We'll also study Laplace equation, and hopefully I'll give you some more insights, maybe more from physical point of view, not mathematical, but there will be some overlap. I don't see this as a very bad thing. I think it's a good thing. The reason why I think it's a good thing, I think people should relearn some part of the old things, because when you go to the exams, many of you don't know the material, so repeating some part of the course is not a crime from my point of view. But the second part of the course, maybe fourth chapter and onwards, and more new material will come up. So we are going to gradually increase the level. So what we are going to study today is chapter 1 in Griffiths. Chapter 2. So you studied already chapter 1, you should read it. It's the mathematical introduction. Now you know already chapter 2 in principle. For next class you read chapter 3 and then you come to class. And that's what will happen. 12 chapters hopefully will end. Okay, if the Iranians will let us, I'm not sure. So let us start now, and the second chapter is about electrostatics. and statics means nothing moves. This is this simplifies the problem tremendously. When charges are moving, which is essentially chapter 12 in Griffiths, things become very, very complicated. And so we start when they are static, when they are not moving. So the general problem is the following. I have some region in space, and in this region I have charges. These charges, you can think about them in two different ways. One way is to think about discrete charges. So these are the electrons, the protons, or some other particles which are charged. It can be a few and it can be many, 1 or 2 or 3, or Avogadro number. That's one way of discrete charges, which are point particles that are, I put them here with a nail, they are not moving, and they are out there in space, in some region in space. Their distribution can be extremely complicated, and immediately you have a problem, because let's say you are composed of electrons and protons, you don't know where these electrons and protons are, you have no idea, right? So how can you solve this type of real problem in a microscopic body? It's kind of impossible. So while for a microscopic problem, when you have, let's say, a few particles, you can think about this type of problem. So how do we treat macroscopic bodies usually? We say instead of a discrete description, we have a continuum. So these are two type of descriptions, and the other one is a continuum. And the continuum is just a smearing of this charge, which means you have a charge density. And we are going to discuss these two problems today. There are some subtleties between these two types of descriptions. So we have here, so what I plotted here, I plotted both. These dots are discrete charges, and everything together may be something smeared out, some charge density. So the question is very simple. Given these fixed in space charges, what is the electric field? And for that you define some reference frame, and you define some point R where you have some observer, and this observer is asking what is the electric field in this place. Now, if the charge is static, as you know from Coulomb's law, and what I'm explaining here is essentially Coulomb's law, if they are static, the position of each charge will give you the electric field here, and then you need to add them. The addition is very complicated usually. You add them vectorially, this effect. If they are moving, you would say, okay, they still depend on the positions, but they are moving, so each time they'll have a different electric time-dependent electric field, right? This is actually wrong, because if they are moving, you are creating not only electric field, you are creating also magnetic field. But it's actually much more complicated. It does not only depend on the position when they are moving. It does not depend only on position. It does not depend only on velocity. It does not depend only on acceleration, but actually it depends on the history. That is, where this particle was in the previous time. And the reason is that the time it takes to arrive here is the speed of light, and that is then becomes a super complicated problem. So what I wanted to say here is that when you have a static problem, things are easy. When they are moving, it's much more complicated. Essentially, it's chapter 12 of Griffiths. So there's a lot of way to go up till there if you want to include relativity, etc. Okay, so now they are static, and we want to know what is the field. And this is essentially a simple Coulomb's law. You know it. But maybe written in a way that I'm sure you saw it somewhere. But now we will define the method of our representation of problems. How does Griffiths describe the notation of our course, essentially? So we have this position R relative to some reference frame, and this is given by the famous permittivity of the vacuum, epsilon 0, and then I need to do an integral over the volume. The volume is this object here, and then I need to have this volume. It has a R prime, so this is the charge density. I'll soon discuss what exactly this is. Then what does Coulomb law say? You have the r, the position of the observer, minus r prime, power 2. And here I have a unit vector. So this hat is the unit vector. And all this I integrate of something I call d tau. This is the famous Coulomb's law in our course. What is rho of r prime? So what is r prime? So you have here some position r prime. Rho prime d tau. D tau is a symbol for a three-dimensional box. It's a small box. Here I have a small box. dx, dy, dz. If you are talking about Cartesian coordinates, r dr, d cosine theta, d phi. You know all these boxes in different units. This is again chapter 1 in Griffiths. We are working here in this notation in 3 dimensions. So the dimension here is 3. Usually we live in dimension 3. But this charge density can be defined in dimension 3, 2, or 1. This charge density is charge, units Coulomb, divided by unit volume. So this is the total charge in a box whose size is delta tau. So the idea of this notation is very simple. We do not like to write dx, dy, dz. We compress things, so we write a d tau. You have to get used to it because we are going to use it all along the course. The total charge in a box, d tau, centered on r prime. So what you have here and here is simply the charge. You see here the 1 over square root term, which is the famous Coulomb's law. It could be also gravitational law, but in principle. And here we have this unit vector between these two vectors, r and r prime, because you know the electric field is a vector. Now, as I go from one point, I go to a different point, different point, different point. I need to sum. And this is written by this integral, where I have this symbol v. And again, I'm compressing these symbols a little bit. I'm not writing 3 integrals. I'm writing 1 integral over the volume containing this thing. And this is essentially the Coulomb's law because of this number 2. The fact that you have here 2 and not something else, and that 2 is related to the dimension, this is actually dimension minus 1, is the one of the most important things in electrostatics, making it a very beautiful theory. If we had here a different number, everything would collapse. Everything what you know is totally wrong. This is a kind of a very nice coincidence that makes the physics really beautiful, actually. So the fact that it is 2 and not something else is a great advantage. I'll elaborate a little bit about this later on. Here we don't have only the Coulomb's law, we have actually 2 laws. What is the second law? What am I using here? It's a bit more than the Coulomb. I'm also using here the superposition principle. The superposition principle says that the charge here gives me an electric field here. By the way, this distance from here to here is of course r minus r prime, which is this one. So this is why this enters here. So the superposition principle says the electric field here is a sum of the electric field contribution from this part, plus this part, plus this part, etc., etc. The summation turns into an integral. So all in all, we have here 2 principles. One is the Coulomb law. The second one is the superposition principle that you add it in a trivial way. Okay, what is rho of r? I said this is the charge density, and you can think about this function as a smooth function. Let's say uniform distribution of charge inside here, or something that is increasing in this way, whatever. That is a smooth function. But you can think about this density also in a different way, which is the discrete way. And that is, what in the discrete language, rho discrete, what is rho of r? It's a sum over qi. R is now as a function of r minus ri, sum I equal 1 till n, where the qi's are some charges, dot charges. Let's say the electron, let's say it has zero dimension. That is the position of the electron. It has the charge of the electron. The electron is in position Ri. This is a three-dimensional delta function. Again, chapter 1 in the book, but I think you saw it. And you see immediately that this is a very strange and very wild density, right? It's not a smooth density, because at each of these points, we have a delta peak. And then if you plug this one in here, what will you get? You are supposed to see this. If you'll plug that one in here, you'll have a sum of the delta functions, and then you'll have a sum of electric fields. The number n is simply the discrete number of charges you have in the system. Let's say you have 20 charges, so that is the number you have to sum. In principle, this is the correct description, but again, we replace it many times with some kind of smooth function. Okay, so epsilon 0 is the permittivity of the vacuum. It's 8.85 10 to the minus 12 Coulomb square over Newton meter squared. So that is important note, which means that we are working with SI units. The standard, that's why we have here this epsilon 0 here. This is the units of the course. So a side remark, you'll have many problems. Here we thought about the body in 3 dimensions. Everybody is in 3 dimensions, even a flat sheet of paper is in 3 dimensions, but we, in many situations, we can take a very thin surface and say, okay, it's a 2-dimensional surface. Just neglect its width. To a good approximation, let's say a membrane of a cell. On the membrane of a cell that's in your body, you have some charges, or a DNA. DNA is an important molecule. It is charged. That will be a 1-dimensional object to a good approximation. The geometry of this object can be extremely complicated, but in this case, I wrote a rho and d tau. Now we have to change the notation because the charges are in 2 or in 1 dimension. The real world is in 3 dimensions, but we can describe, let's say, a surface, a membrane. So this is a surface. Or we can describe, so this is dimension 2. This is dimension 1. So here I have some charges on this spaghetti. And here I have other charges somehow. Smooth, I'm talking about smooth things, not about discrete things. This will be described by lambda. This is the charge per unit length. And this one, the surface, will describe by sigma. That's the charge per unit area. So this rho is charge divided by volume. This is charge divided by meter squared. This is charge divided by meter. And then you need to replace this integral. Instead of rho and instead of over a volume, you need to integrate, let's say, in 1 dimension over this line, complicated line. So the integration will be here over dl usually, and this will be over dA. And you need to know how to translate this formula into those formula for those special cases. So the number of exercises that we can give you is very large. And these integrals are very complicated in general. Generally, you cannot solve these integrals, but then you can solve them numerically. You know, if you have a twisted polymer or something like that. If you have symmetry, we do something else. Usually when you have a symmetry in the problem, we don't use so much the Coulomb's law. We use Gauss law, and we exploit the symmetry of the problem with Gauss differential or more integral to Gauss law, which we'll soon discuss. So there are several ways to solve these problems, I think, as you well know. The next thing I want to say is, okay, I introduced the solution to the problem. And because of these angles that are changing as I integrate, this is a complicated problem. And then thank goodness we don't, we can solve it differently, and the way to solve it differently is using a potential. So the electric field, given by Coulomb's law in general, has three components, let's say Ex, Ey, and Ez. However, these components are not independent one of another. So you don't need three functions. In principle, you have here Ex. These three functions are function of X, Y, and Z, and you need to calculate them, right? What does a potential field say? You don't need to calculate three functions, you need to calculate one function. So we are reducing the problem by more or less by 3, which is a good thing. So these are not independent. And the reason is actually comes from Maxwell's equation. So we'll talk later about Maxwell's equation. But if we assume Maxwell's equations, it also comes from here. You can also prove it from Coulomb's law directly. But Maxwell's equation, the Faraday equation, says that dB dt. Now, this equation is 0 when the fields are static. Nothing is moving, so the time dependence of the magnetic field B is gone. And that means rotor E, or curl E, is equal to 0, and this is important. And this means, because what are these? This is the derivatives. What is rotor E? So rotor E, let's say in Cartesian coordinates, again, all this is in chapter 1, and all this I think you know. So, okay, let's write it as ddx, ddy, ddz. Okay, so this means, and I'll show you why in a second. This means that E is equal some function V, which we call the potential function. And here we have, what is this symbol? We call it nabla. Why is it called nabla? Do you know? Comes from? Nevel, yeah. Which is also in Greek. This is this nabla in the Greek is nevel in Hebrew. So this is what people think. Sometimes it's called del, and it's now acting on a scalar. So there are many different names to the, when you use it here, this nabla, you use it here, then you call this a curl or a rotor, etc. So there are different, there's the gradient when you act on a potential, on a scalar, and if you act on a vector, this will be a divergence. So all these names are a little bit confusing, just refresh your memory if you don't remember them. So here we have the nabla, and this is the gradient of the function v, which is a function of x, y, and z. So if this is true, then I'll show you why it's true. Then here I have d dx v, here I have d dy v, and here I have d dz v. I take here the determinant, so let's look only at the first guy because the rest are the same. And then I have here d squared dy dz minus, because of the determinant, d squared dz dy, and the functions, you can replace the order of integration. And then this guy is 0, and then this is 0, which is exactly what I want. So every function whose rotor is 0, I can find another function and represent it like this as this potential field. And then again, the point of view is, taking this gradient is easy. This is like nothing. I mean, take the derivative, okay. So we will calculate this function many times. This happens in Poisson equation and Laplace equation, which is next. We will study the next lesson, and the hero will be the potential because of its relative simplicity. You're going from a vector to a 3-dimension. Now this is all fine, and this I guess you know all this, but how can we view this kind of more intuitively from the field lines? I mean, or maybe we can discuss it a little bit. So let us discuss field lines and understand this equation This is simple mathematics, which is fine. Some people will say, okay, you understand everything, but let us discuss it a little bit. Why rotary is equal to 0, how do you see it from field lines? So I'm going to discuss the simplest field line, and let us think about the field lines, because actually they are not trivial, and they are also related to the fact that Coulomb's law, 1 over R2, and that we are working in 3 dimensions. Let me try to explain this. Because let's say I have here a charge. This is very simple, Coulomb charge, electron or something like that. How would I describe the fields coming out of this? So we know the answer is 1 over R squared, and the direction goes outwards, right? So how to plot it? The question is how to represent it. So I can start by plotting the directions. And you know, if this is a positive charge, these are the directions, right? What it means that if I put here a test charge, the force will be positive, positive, you will go like that. But now this figure, does it show you the magnitude of the field? Now what do we know? We know that here the field is very strong, and far away it's slow because it's decaying like 1 over R squared, right? So if I would be the first guy, and maybe also you, because you live in this world that the color is nothing, I would say, okay, let us have here, let's put here some color red, something like that. And if you have red and it will go down, if it will be red, it means it's very high field. And if it's low, it's low, right? And then you need to plot it. But if, I don't know, Coulomb didn't live with a printer and it was difficult to plot it like this, assuming maybe someone plotted it like this at the beginning, but then you say, okay, but do we really need the color? Do we need the color to represent the field? And the answer is no, we don't need the color, which is a bit weird at the beginning. We can think about these simple plots. So here is the charge, and this tells me what is not only the direction, but also what is the magnitude of the field. And what is the rule? The rule is, let's circle here some circle. Now this circle is actually, I'm plotting it in 2 dimensions, but actually it's a sphere. It's coming out of the board and in the board. It's very important that it is a sphere and not a circle, actually. Because we work in 3 dimensions, that's my point of view. And we look at this surface and we look at, okay, we know that the electric field is identical in magnitude on this radius. And what we do is we look at the density of these lines. So here I have some sphere, and then let's look at another sphere out here. So this will be small sphere, S is small, and this is big sphere. And it's easy to see, if you get used to it, that the density on the small sphere is larger. The density of these lines is larger, right? The density on the big sphere is lesser. Now what do I mean by density? It's just the density of what I plot. You can think about it, there are millions of curves like this, but I decide, because I'm lazy, to take this charge and just plot these 8 curves, then the density here is different than the density here, there. And then here, if you have a high density, field is strong, low field is weak. But is this also really quantitative? Is it really exact? Because let's say 1 over R to the power 3 was the Coulomb's law, then this will be maybe intuitively correct more or less, but it wasn't exact. The reason is very simple. What is the density of these lines on big versus density on small? Now, The density, what I mean, you just count how many lines are crossing this sphere and divide by the area of the sphere. What is surface area of a sphere, you know, from high school? It's pi r squared. So this one is pi r big squared, and this is pi r small squared. Pi cancels. Also the number of here 8, but there are more because it's also going out. The number is also cancelled because that is the point. The number of lines crossing these two surfaces is exactly the same, of course. And then you have this ratio of the square. What is the ratio of the square? This is exactly the ratio of the electric fields, right? So this is simply the electric field at B in magnitude, the electric field at small. Now, why is this possible? It's possible, you see here, because the dimension we are working in is 3, and then the surface is r to the 2. And also because the electric field in Coulomb's law is 1 over r squared. So because they are the same, you can forget about colors, and you can plot it only with very simple lines and nothing else. Again, emphasizing my point that the dimensionality here, 3 minus 1, and this 2 here makes something very elegant and simple. We don't need colors, and then we can plot these field lines even without colors, which is great. Today, you don't think about it because you think, oh, we can do it with colors, but who cares? But this is how this was constructed a long time ago, these field lines. And now we can go back kind of visually to this rotor E equals 0. And again, just working on with one charge. Now here, maybe you need to read a bit or think more. The question is this field that I'm plotting here, what is its divergence and what is its rotor? Well, we know the answers. The rotor is 0. But any field, let's say these are velocity fields. Let's say you have a sprinkler and the velocity of the water going out in these all the directions. This type of picture immediately says that rotor V is equal 0 because there's nothing rotating here. If I had a picture like this, some field, again, it's not an electric field. There's no electric field that goes like this. Here you have a rotation, right? So if I look, for example, if I have, let's say, person 1, and his hair goes like that, another person whose hair goes like that. Of course, these are not exact expressions, but here, this whatever, it's a boy or a girl, it's a curly guy, right? It's a curly, you know the word curly. Curly means hair curls. So here the curl is not 0. Here the curl, well, it might be existing because I'm not plotting, but here there is a divergence. Your hair is diverging, right? So here there is a divergence. Now here there's also a divergence at the middle. Yeah, hopefully you can see it more or less with your eyes. What is the divergence here of the electric field? You should know it.
Can you repeat the question?
What is the divergence of the electric field here on the origin?
Inverse square root?
What? No, of the electric field. The electric field is inverse square. What?
1 divided by the tension. No,
Forget about 4 pi. Yeah, delta. Someone said delta. It's a delta function. Why is it a delta function? Okay, we'll soon see. That comes from Gauss' law. The fact that it is a delta is related to the 1 over r squared, that it is actually a delta. I'm going to explain this again. It's all because of the 1 over r to the power 2. So here we're going to have a divergence, which is a delta function. Let us discuss this also a little bit. So-
Excuse me,
Yeah.
can you explain what is the divergence, please?
Yeah, we are going to describe it a bit more. It's essentially the nabla operating on a vector. Okay, so now what I'm describing here is my maybe not so good intuitive way of thinking about things, but you need to think about it more. But you also need simply to take, for example, some fields and apply them, let's say, not only in x, y, z, but also with, for example, with cylindrical coordinates or with spherical coordinates. To see this, just plugging in some fields, go to chat, give him some field and ask him to explain why rho to v of this electric field in spherical coordinates, in cylindrical coordinates, why are all the terms going to go away? You'll see that it's a bit interesting in the sense that the electric field is only in the r direction and it only depends on r. So any field, not necessarily electric field, that depends only on r in directionality and only on the function r, its rotor rule will be 0. So because you see here, this comes from a very general requirement. There's no physics, there's no charges here. So this requirement is just a kind of constraint on the electric field. It's not giving you the solution itself in the sense that it's not addressing at all the charges. There's no, I didn't discuss what are the charges here, at least not directly. So now we can go, or you can have in Griffiths, you can have more intuitive way of thinking about fields. Let's say you have a positive charge Q and a minus charge Q, and let's plot the field lines. So what do? You say, okay, these guys are far away. If I go very close, what will happen? If I go very close, the electric field due to this guy is going to be relatively small compared to the one created by this charge. So in the vicinity of this charge, it's just like a single charge, like what we had before. And this is a plus charge, so it's going to go like that. What will happen here? Exactly the same, but in the opposite way. So the rule here I plotted the 8 lines. I need to do the same. I cannot just change the number of lines. But it is again will be an isolated object. And the arrows is the opposite because now we are dealing with a negative charge like that. Now, if you continue these lines, what will happen? This line will go like that. This line go like that. This line, I'll make it a bit bigger, like that, etc. This is actually going down to very far away. This is not a very good drawing. This line will go to infinity. Not all lines will close. Not all lines close. Some of them close and some of them don't. But what cannot happen to these lines? They cannot cross each other. Why can't they cross each other? It's very trivial. Because if they cross each other, then where is the direction of the electric field? Is it this way or that way? There's one direction to the electric field, so these lines do not cross each other. Now you can look at this picture and let us look at it in this direction. I'm going from top, in the middle, between the charge, and then down bottom. What do I see here? I try to show you. Up here and down here, what is the density of the lines? It's kind of separated more and more. So the fields down here and up here, you see with your eye, are less and less. In the middle, the density is a bit stronger. again, you go to the book if you want to see better pictures. Why is the density here bigger? This is what we said before. Wherever the density of these lines is high, then relatively to the other places on this plot, the electric field here is larger compared to this guy. But if I compare the density of these lines here compared to what I have here, then obviously here is the higher density, and this means that here is the higher electric field because we are close to the charge. That's also trivial, but this allows you kind of to visualize these fields. And again, I said the divergence around here, well, it's the same as the single charge. It has to be a delta function here, like the single charge, because there's no the electric field here is just this one, and the divergence here will be also a delta function, because again, the electric field is only coming from here. Okay, so now let us see this issue with the divergence a bit more mathematically, but before doing that, let us summarize essentially all what you need to know from electrostatics. So Griffiths gives us a kind of roadmap, if you want, which is a triangle. What is the time? Okay. In electrostatics, operationally, we have three objects of interest, which are related one to another, and the potential. This is not volume. And all the problems are, usually the problem is, give me a density, or a charge density, or a unit surface, whatever, find the electric field, or give me this density, find the potential, then we go to the electric field. These are the general kind of problems. And we already discussed how to go from here to here, right? This was the equation 1, that is the Coulomb law. We had already this integral, equation 1. Sorry, give me rho, I can, in principle, find this way. If I want to go the opposite way, well, one thing you need to satisfy is that this rotor A is equal to 0. And the second one, which I'm going to discuss a little bit more in detail, is if E equal rho divided by epsilon 0. This law is actually equivalent to the Coulomb's law and the superposition principle. In Maxwell's equations, this is part of the Maxwell equation. So this gives you the following option. For example, if I know the E, if I can take the divergence, this is defined here, I can go in that direction. And I can also go in other ways. That is, if I want to go from V to E, I explained this already. So E is equal minus nabla V. And the opposite, and this I'll also explain, is simply, okay, so this we said. So what is going to be the opposite thing? Going one way is a derivative. Going the other way is going to be an integral. There are some subtleties on the path of the integral, but this is simply this equation, which you know that this is V, the potential is minus EDL along a path. And the whole issue is that it doesn't matter what is the path. If you want to go to a specific position, it doesn't matter what is the reference frame of the potential. Usually we take that, at infinity the potential is 0. But these two laws, I explained this one, and this one is, in my opinion, intuitive. It's simply the opposite in opposite operation, if you want. And then if you want to go here let's say this way. How do you go? What is the equation that brings you from there to there? The equation is the Poisson equation. It's easy to derive. It all comes from Coulomb essentially. And the opposite way is another formula which is very similar to the formula that I give you equation 1. Sorry, this line is the opposite way, in the sense that if I know the potential, I can get to the density, but if I want to go the opposite way, then as you know from high school, the potential will be not 1 over r to the power 2, it will be 1 over the r. And then the more sophisticated way to write it will be that the potential is 1 over 4 pi epsilon 0, some integral, like we had before, of rho d tau r minus r prime. This will depend on r prime. So this will be, there's no hat because V is not a field, and you need to add up contributions from potentials that you already know in other courses. It's just adding many of them to get this potential. And again, this part we will discuss later on. I'm going to now discuss essentially this part we discussed already. I want to discuss a little bit more now this part, these trajectory integrations of different trajectories. So
the rho is positive, right?
the rho it depends what type of charge you have, but yes, I mean if you think about positive charge. So let us discuss a little bit the integration of a path to get potential, because it's important also for physical consequences, which are, for example, for work, how much work we need to assimilate a system. So I'll use here Stokes' law. Stokes' law, again, it is explained chapter 1 in Griffiths. It's a mathematical theorem. I'm not going to prove it, and you heard about it before, but I'll remind you, and I'll just show you how to use the Stokes' law in order to get some insight in physics. So according to Stokes' law, the integral over a surface, so maybe we should write it surface. So what is this surface? Some surface. It's not a physical surface. It's an abstract surface that I decide to put somewhere in space, wherever I want. Okay, so many times this is a bit confusing. You have a physical surface and you have a mathematical surface that you just use for some explanation. So this is my surface. The integral over the surface of rotor E, that's a vector dA. dA, again, I briefly explained it before. This is an element. If you want, dA is this element here in the surface, and you need to sum up all of them. And dA is normal to the surface. So that's the definition of dA. And what you have here is take the rotor of E, multiplied by dA, and sum up where this is the dot. So this is a vector and this is a vector, you need to sum this. Again, doing this might be very complicated, but in this case it's super easy. Why? For the electric field this is easy, because this is equal 0, so this is equal 0. Because of what we said before for Maxwell's equation. But this, according to Stokes' law, is an integral over the perimeter EDL. What is the perimeter? It's the perimeter of the same object, according to Stokes, and I integrate it. So I need to know the value of the E. It's a very nice theorem in general. I need to know the value of the electric field not inside. Let us assume this was not zero. I need to have the information on the rotor inside. Everything is here. I need to sum up. Stokes tell you, no, you don't need all of this. All you need is to go on the perimeter. dl is the perimeter. So what is dl? This is dl. And then you sum over that, and then you get this answer. And you see more or less what is happening. Here I have a kind of two-dimensional integral. Here I have a one-dimensional integral. And the reason is because here I have the derivative, so I kind of do one integration, so to say, and get rid of this horrible rotor, and then I do just this thing. So this means that this guy is equal 0. Okay, fine, and I think you saw this, and this has consequences, for example, for the potential. Because what does it mean physically if I have some path, and I have a point 1 and I have a point 2 along the path? So the integral from here to here, the line integral, EDL, from 1 to 2, when I'm going up, this is, let's call this path 1 to 2. And then I have another integral that I go down. Two to 1, EDL. Again, along this path now, this is equal 0. So if I take this to the other side of the equation, and I change, instead of going from 1 to 2, I'm going from 2 to 1, I go from 1 to 2, the integral will be independent of the trajectory that I chose. Whatever integral I chose, I'll have the same result. It doesn't matter. Independent of the path. Okay, it's independent of the path. Now we want to do two things. First of all, why is it important from physical point of view? First of all, it's a constraint on the electric field. Of course, this is very nice. But also, if I have a charge here walking here, the electric field that this charge is feeling gives you the force on this charge. And then the path that it goes in here, which is the force along the path, is independent of the path. So this is a nice thing. So, usually this is a conservative type of thing that independent of what is the path, the work you do by moving this charge from here to here or from here to here, and these two very different trajectories is the same thing, right? Because it's independent of the path. This is not so obvious in systems with friction. This is not correct. So the work going from here to here and there to there is going to be the same. And you can, of course, distort the path because this is just a mathematical construction. You can have anything that you want. But now the question is, okay, we have all this math and this is also known. Let us go to something visual and try to understand this rule from with your eyes or with your guts or whatever you want to call it. Everyone has a different ways of thinking, of course. So let us look at the simplest case, a single charge. I have a single charge. And why is this integral EDL is going to be 0? So here the philosophy is simple. Let's look at one charge and prove that the integral when you go in a circle or any path is going to be 0. Not prove, just try to understand why the field lines give you this or why it's obvious. After I looked at the single charge, I can use a superposition principle. So if I have many, it doesn't matter. So it's enough to look at a single charge, and then if the electric field satisfies this EDL equals 0 for one charge, then you add another charge, it also adds, and then you're done, right? So we can look at one Coulomb charge here in the origin. And let us see with the eye. So we have the field lines. And let us do the easiest thing. What is the easiest thing? The easiest thing is to look at a circle. But that's only one path. This is the circle I'm going around this charge. חוני המעגל. It's trivial that the direction of the field here is E, is outward, and dl, hopefully you see, is like that. What is E dot dl? And every point along the path is equal to 0 because it's 90 degrees between them, right? So, okay, so here, let's write it, E is dl, and then it's trivial that E dl is equal to 0. Okay, now let us work a little bit harder, and let's see what happens when I distort this path. If I distort this path, okay, I will... The difference between mathematics and physics is that, at least when you build intuition, in my opinion, you start with one example. The mathematicians prove it in general, which is much more powerful, of course, but we are not interested in that. So let us have this charge here, and let us invent a crazy, or what I consider crazy path. No, this is going to be a very bad plot. Excuse me. Is this the center? I can't see. This is not the path. More or less the center. So I'm going to use a path. I'm going to be lazy, so I'm going to use this path. Okay, this was like what we had before, right? So now we should do something more interesting. Let's go like that. Something like that, and then backwards. This is again a radius here. This is on a circle whose center is here. This is also on a circle. I go like that, let's say like that. Is this complicated enough? I go backwards. Let's take this one. Now, again, what is this? The black line is simply the path I'm integrating, the electric field that is caused by this one. I assume claim that for a physicist this is a general, this is a proof, a physicist proof. You can catch me where I kind of small cheat, but it's not a cheat. You had a question?
Yeah. Is it related to the fact that you can introduce the electric field as a gradient of a scalar field, and then you say that a closed integral of a gradient is 0?
Yeah, but the way I see it is exactly the opposite. That is, the integral rotary is the center because it comes from Maxwell. Then EDL is because of Stokes. And because of that, you can have a potential field. But it's all circular. You understand it's all circular. But because we consider Maxwell as the big boss, I would say, most physicists would say this is the starting point. I'm just making things connected. From a practical point of view, you can say they're all the same thing, right? Okay, so we have this crazy path, and I'm integrating along this path, and then let's see what happens. So when I integrate over here, what is the result? That's 0, like before, because the electric field goes outwards and dl is that way, so it's orthogonal like we had in this example, so it's trivial. Now we have this part. So first of all, along these arcs, EDL is going to be 0 because I choose a kind of a radius here that goes like that, right? So only thing is left is going on this path 2, 3, 4, okay, 5, whatever. Now, how do you see from this picture that the integral over the remaining 1, 2, and 3, what I mean by this is here. I go here, I go here, I go here, I go here. Why is this integral going to give you 0? What? They are cancelling each other, and you can easily see with your eyes where they are cancelling each other. So, for example, this point is cancelled by this point, right? Because the field is exactly the same at these points. And then this point is cancelled by this point. So first of all, the sum of these vectors, L1, L2, L3, L4, and 5 is 0. But also each point has a corresponding one here. So in short, EDL is equal 0. Quite easily from this picture. Now you can say, but this is not a proof. So I say you can go to a mathematics department. It's not a proof because I used here this kind of arc, right? I didn't put it in a straight line. But what you can do always is you can make this into small, very small little arcs. So any object that I want in the world, I can more or less, not rigorously, I can build a small kind of arcs around the center and some line, and then it should be given by that. Okay, so it's a trivial issue that EDL is equal 0, and from there we get the potential. Maybe I didn't write the equation, V of R, but this is related to this, of course, that V of R is EdR along some path from 0 to R prime. The path is not important, as we said before. There is a small issue, and that is the reference, but that is a convention. So usually we will take, okay, the potential at infinity, if you have a charge, is 0. But this is something you know. You can always add to the potential some constant. The reason why it's not important is that eventually what you care about is the electric field, and you're taking the gradient of the potential to find the electric field. So the potential, as usual, is defined up to some potential. But there are some conventions that most physicists use, especially that infinity, the potential is usually taken to be 0. Okay, so now we have, I mentioned in this triangle that we had before, we had the Gauss laws, which again, you know about them, and I'm just trying to help in some discussion, or remind you, whatever. We have the Gauss law, and we have two Gauss laws, right? You remember the two laws. One of them is an integral law, and one is a differential law. So let us talk about the differential law. Gauss. Differential. So essentially, I think Gauss was a German, Coulomb was a French guy. Maybe Coulomb should be really upset because it's essentially the Coulomb law. But he formulated it in a very nice way. Gauss, I mean, well, one of the greatest, let's say, in many ways. And with his formulation, we could solve many problems in high school already that exploit symmetry. So it's not just an exercise to go from Coulomb to Gauss, but physically it's the same. And this you can see in the following way. So what I'm going to do, as usual, I'm going to reduce the problem to Coulomb. I'm having only one charge. Let us look at this, and then with superposition I can make it something. I'm actually even not going to do that. I'm going to look at the divergence of E. Now some guy asked me what this is. The nabla in general is dx, dy, dz. I'm sure most of you know this. And then I'm operating on this electric field with this operator. So each component, dx over ex, dy over ey, etc. This you know, and again, if you don't know, then I don't know what to say. You should ask your money back from first year in physics, or go and read Griffith's number 1. So we know the electric field. That was this equation 1 that I had here before. So let us just apply this to the electric field, because we solved it already with the superposition with Coulomb. So what did we have? We had rho of r prime. We had this d tau. we had r minus r prime, r minus r prime, to the power 2. The 2 is again very important. We had the integral over the volume, and we had 1 over 4 pi epsilon 0. So again, what we have here, like before, we have some charge density, rho, of r prime. So here is the reference frame. This is r prime, and then I have another r where I look at the electric field. I have rho of r d tau, that is the charge. This is Coulomb's law, the inverse square law. And of course, these are vectors. So r minus r prime hat, that's a unit vector in this direction, right? And I need to sum all of this. But now I added this divergence, right? It's a divergence, it's a nabla, but it's a divergence because it's acting on an electric field. So I'm looking at the electric field at some point r, and I'm taking this operation on it. Now, when you look at it, where is r in this equation? It's here. See this object? It's not in the r prime. It's not in the d tau prime. That's the integration over the volume. Now the question is, what is this object? What is the derivative of this? This is with a dot, of this guy. You should know it as mathematicians, and you should know it as physicists, if you know basic electrostatics. So what is this thing? What should it be? You know the answer. Well, you should know the answer. I gave you the answer already. What is this integral? All this integral. What should it be? You are right. This is a delta function. But why is this a delta function? Because the whole solution is rho of r divided by epsilon 0, right? So how do you get out of rho of r prime in an integration over space here, rho divided by epsilon 0? Remember, that was Gauss' law. This guy, damn shit, it has to be a delta function, right? Otherwise things will not work, right? So you know the answer as physicist. So this means that if I prove that this object is a delta function in 3 dimensions, then I'm done. Okay? So this is equal rho over epsilon 0. It's not exactly a delta function. You'll have 4 pi. 4 pi times a delta function. You need to cancel this. So, okay, we can, maybe we will prove this actually. A mathematical statement that this is 4 pi delta 3 r minus r prime. You could say I take it from ChatGPT, and you can check it for yourself. And we will check it because actually checking it is worthwhile. So this is a delta function. I do an integral of a delta function, and then I get rho of r dot e, rho at point r over epsilon 0. Notice that this equation is, I'm applying the divergence on what? Forget about the 1 4 pi epsilon 0. This is the electric field in physics of a single charge. That's what it is. So if I have here only one charge, this is a delta function by itself. You have here 2 delta functions, right? If it's a single charge, rho of r is a delta function. Then what you see here is, according to this law, if I have a Coulomb, one charge, I take the derivative. This is exactly the form of the electric field that you know from high school, Coulomb. It should give you also a delta function. And this is correct. Why is this correct? Because if you have one charge, it's located in one point in space. That gives you a delta function type of charge. It's 0 everywhere except for one point. The integration over the density gives you the total charge, right? That's the meaning of this delta function. So you kind of know it, more or less. You know it from a single charge. It's kind of obvious. And here is 3 lines of algebra. We went from Coulomb to Gauss. Gauss in the differential form. Differential means that I'm taking a derivative of the electric field and not an integration over the electric field. But why, let us spend some time on why this is correct, because this is essentially everything. It's the divergence of an electric field of a point charge, and it gives you this simple connection. And as I already mentioned, the reason is that we are working in dimension 3, and in Mr. Coulomb gives us 2. The 3 and the 2, they come together, they create some magic. If this will not be the case, all this will be totally wrong. And then you will be in kind of problem, not because of this law, actually because of the integral law, which is the law that helps you solve problems with symmetry. So let us look at this briefly. I want to prove, I'm going to eliminate this r prime. But so I just say r prime is 0. So what we want to look at, or what we want to claim, is that this guy is equal 4 pi delta r. It's delta in 3 dimensions. Maybe you saw this before. Did you see this before? Okay, you're quiet. So we will show it again. So here I just took r prime equals 0, but that's only a shift. I don't care about that. So, okay, so the basic rule that we're going to use soon is the divergence theorem. So, and then I need to remind you what is the divergence theorem. The divergence theorem of some vector v. V is some field. Think about it as velocity field. It's with a vector, so it's not a volume, and it's not a potential. I hope you don't mind me using this v. Let's call it speed or velocity. Some field. This is all mathematics. D tau. So the integration is over volume, like before. Some volume. It's mathematical, so you can define whatever the volume is. The volume has a surface. This volume, like before, has a surface. So you see you have here a derivative, then you get rid of the derivative, and instead of integrating over the full volume, you just need to integrate over the surface, which is a huge simplification, and the integral over surface is v, which is a vector, dot dA. This is over the surface of this object, whatever it is. Okay, this is the divergence theorem. So let us prove more or less that this is the above is a delta function. So what is a delta function? Okay. Delta function, intuitively at least, if I'm not looking at r equals 0, far from r equals 0, r equals 10 is 0. So let us first of all check that this is indeed giving you 0 far away from the origin itself, and then treat the origin itself a little bit more carefully. And this is very easy because it's not related to the divergence theory. What you need to do is look up what is the divergence in what coordinates shall we use. Obviously spherical coordinates because of the symmetry of this kind of Coulomb potential. Again, this is a Coulomb potential. If I add a 4 pi epsilon, it's the same. Then I just have to look it up, and this is easy because it's also in every book or whatever you use. R squared. Oh, okay. Let me write it in general. Over some field v again velocity, and this is 1 over r squared. D dr r squared. This square is so important. V of r. What is V of r? V of r is the component of the vector v in the r direction. The vector v has three components in spherical coordinates: the r direction, the theta direction, and the phi direction. Shall I write it on the board, or you remember this? R, theta, which goes, the cosine theta goes from up here to down here, and then you have the projection, you have the phi. Phi angle, phi goes between 0 and 2 pi. Theta goes from 0 to pi, and r goes from 0 to infinity. And this is the way we define this Cartesian coordinate. And this is the first term, and then there are other terms which are related to v in the phi direction, v in the theta direction, but I don't write them because they are all 0. You can check it out for yourself. They're trivially 0. They're trivially 0, sorry, for this field. Okay, maybe I should write it. But it just, eventually there will be 0. So for example, we have all kinds of nasty things. We don't like them. d theta sine theta v theta plus pak. This is not relevant for us because the electric field, this field, is in the r direction. There is no component in the theta direction. So this one will go away, and the only thing that will remain is this one. But this one, for this particular problem, v of r here is simply 1 over r squared, is simply 1 over r squared, d over dr, r squared, 1 over r squared. This is 1, this is 0. When you have r equals 0, then 0 divided by 0, you should be more careful. So this is for any r not equal 0. So this is like a delta function in that sense that this function is 0 everywhere. Maybe there's some problem on the origin. Now we want to prove that it is a delta function. How do we prove that it is a delta function? Here we will use the divergence theorem, more or less proof. And then the integral of a delta function, by definition, is what? Integral over the volume, over all space, for example. That includes the point 0. So for me, this is a definition of a delta function. The more precise definition, multiply this by some general function and see that you get out the value of the function at this point. This is a property of a delta function, and it's a very kind of strange function because it's 0 everywhere, as I showed you, but this integral gives you 1. So it's very strong on this point. It's not the full proof, but if you want the full proof, add here some test function, and then you get the test function out. So let us see that this is happening. So let us define some integral, I, and we need to integrate over the volume of all space. Volume, this is not velocity. R squared d tau. And now you see that this is the same that we have here in this divergence theorem, but now this v is a very special function. And luckily I can replace this with what? With an integration over the surface of this volume. Easiest thing to think about is some volume which is a sphere. Let's choose a sphere. We can then take the sphere to be infinity, it's okay. Then this is equal integral over a surface. I'm integrating over the surface of the sphere, like here. And here I have r. This is my function. But now the point is, by integrating over the surface, I determine what is this r. It's the value of this radius on the surface, which is a circle. So here I have r squared. And then I need to do dA. What is dA? This is an element on this sphere. What is the direction of dA?
Out of the sphere.
Out of the sphere, normal to the sphere. We have this dot, so it's in the same direction of this r hat that we had here at the beginning. So we now need to solve this very simple integral. And let us remind ourselves, what is dA? Again, this is chapter 1. So dA, again, this is a vector, and its units are, it's given by this famous equation. I'm not proving this. Sine theta d theta d phi r hat. So this is an element of surface on the sphere whose radius is r. And the whole reason why I bother with this is this. Ooh, it's the same color. You see here the 2. That's my main point, actually. Why is this 2? This is because we are working in a three-dimensional world, right? This dA is the surface, and the surface in a three-dimensional, you have here the 2. And the 2 here and the 2 here cancel. That's what I said before, that the Coulomb law is 1 over r to the power 2. And these two things cancel, making things very easy and very beautiful and simple physics. If I had here a different law, r to the 3, so first of all, this law would not be valid, and certainly not here also. It would depend on r, but here we have cancellation of this r. And what is r here? It's just some number that I took just to prove something. Okay, so let us do this. So this I is simply r squared over r squared, which is cancelled, of course. And then we have here simply integral d cosine theta from -1 to 1. This is the same as sine theta d theta. It's the same thing. Integral over d phi, I said before, this is from 0 to 2 pi d phi. This is equal 4 pi. This is exactly the 4 pi that we were looking at. So just to repeat, what we proved is that this function is equal to this one because the integral over this function gives you 1 and it's everywhere 0 except at the origin. This was the proof. And again, to repeat, this is because this we choose here the number 2 and here we have 3 for the dimension 3. These two things come together and give you some very nice result. Then we go, for example, here, and then we get Gauss law from Coulomb's law. Everything falls apart from this mathematical theory, but as a statement, as a physicist, it's also a trivial statement, because if I think about this as an electric field of a charge point, the electric field of a charge point comes from a delta function in the sense that if you integrate over it, it also depends on q and 4 pi epsilon, of course, but if you integrate over it and you think about it a bit, this will give you the charge of the point charge that gives you this electric field. So all in all, I think everything fits in very, very, very simply. So now, before we have a break, let us. There were no alarms. Let us just wrap up 2 more small things. I showed you the differential law of Gauss, and now we want to look at the integral equation, because as I mentioned already, in practice we use that equation for problems with symmetry. You did that already in high school, actually. So the integral equation is very important, and let us see how it works. It also is based on the divergence theorem. So the divergence theorem for some, again, V is some vector, whatever, d tau over a volume. So now you are getting used to my notation. D tau is always dx, dy, dz. It's some volume that I have, something. That's one of the reasons of this volume. So it's in 3 dimensions, is equal to VDA on the surface. Later I'll just use V here and S here, S for surface, V for volume. So the surface is the surface of this volume that you are integrating. This is, again, the divergence theorem. So all we need to do is, let's take V and say this is E, the electric field, which is given by Coulomb's law. Okay, so I have here the integral over the volume, some volume, whatever you want. dV was going to be E d tau. But what is dE? We showed it already. That is rho from the first Gauss law. That's rho divided by epsilon 0. So this is rho of r prime d tau over epsilon 0 over the volume. But what is that? The integral, it's a very simple integral in principle. The total integral over the volume is simply the charge of the volume, or the charge of the system inside this volume. So this is just Q enclosed. What is enclosed? Enclosed means the charge that I have inside my volume, whatever it is. I can define the volume different ways. I can make it small, big, then the charge will be more or less divided by epsilon 0. So far I just used the physics. Now let's use the math. This is also equal E dA over the surface. What is it now? The physical surface is the surface that contains this charge. You decide what it is. It can be anything. So I have here some set of charges, very crazy maybe, and I build some box. Some of them might be outside, some charges might be outside. I have some electric field along here. It might be very difficult to calculate, but if I take this surface and it's in 3 dimensions, the surface is in 2 dimensions inside the 3 dimensions, so it comes out, I circle it. And then I take every point, there's some electric field. For example, I measure it. So this is very nice. Let's say I have here charges, and then this thing, let's say I'm here in this room, and I circle it with something which is of the size of the state of Israel. In principle, in practice it doesn't work. And then I just measure the electric field along the outer surface. And then I integrate. It tells you how much charge you have inside. You don't need to be close to the charge in order to know how much charge. This doesn't tell you where the charge is, but it tells you how much is enclosed in this box. And you can create many different types of box. So this is called the flux. And this enclosed is divided by epsilon 0. Now this law is, you used it in high school to solve many problems. It may be not exactly formulated this way, but it is exactly the same. Here it's a bit more general than what you had in high school. For example, if you have a sphere and on it some charge, you put another sphere and you actually calculate the flux outside, and then you can calculate the electric field. If this integral is easy, people in high school solve it all the time, exploiting the symmetry of the problem, if there is a symmetry. So there are 2 types of problems. One of them is simple problems, where you can kind of guess something on the E, and then you can do the part of this integral, and you define the surface by yourself to make this easy. And there are other problems which are hard problems that you cannot do that. But for example, let's say you worked hard, you solved the Poisson equation, you found out the electric field, but let's say in your numerics something might have gone wrong, or maybe you measure the electric field and you measure it over one surface, and then you measure it over a different surface. The first one is inside the second. Let's say you know that all the charges are in the first surface. You are not sure if your measurement device is good enough. So you know that this integral will give you the charge inside no matter what. So you can check things. You can check numerical solutions. You can check experimental results if you're lucky. So this is value also in very complicated problems. where these integrals are not easy to do, but still they give you some conservation law because the total flux here is equal to this total charge inside. Okay, so, and this equation, just to sum up, what's its name? The Gauss integral law, because you have an integral. Okay? Now, okay, but you see everything here is actually, everything is a Coulomb law, essentially. And now we mentioned in our triangle, we mentioned Poisson and we mentioned the Poisson, which goes from the potential to the density, which is again very useful because the potential is not a vector. We don't like vectors sometimes. Usually we don't like it, but that's very easy to derive. To solve is not necessarily easy at all. So we have this definition. Why is this definition correct? It comes from the fact that the curl of E is 0. We reached this conclusion. That is from Maxwell equation, it comes. We also have this equation, which is called Gauss, the differential law, which is also part of Maxwell equations. And then all I need to do is apply the nabla on this equation, and then I have nabla. I have this gradient squared. What is the gradient squared? What will it? Laplacian. Laplacian. So there are many French people and a few Germans. So this will give you these two together. Gives you minus rho over epsilon 0. I hope you all see this. I just operate with this lambda squared. This is the Laplacian. Laplacian, as you know, let's say in Cartesian coordinates is this operator. Sorry, this is Poisson equation. What is Laplace equation?
When it equals 0.
Exactly. So when this is equal to 0, which at first sounds very silly. What does it mean? The charge is equal to 0. So where's the physics? But we will solve the Laplace equation when the density is 0. How come? What physics exists if this is 0? What does it at all mean? Just to remind you on
Conservation.
It's like
it's where you are,
yeah.
not at home. Yeah, I'm listening.
What?
Okay, I was kidding.
It's like in a zero potential field, not zero potential field, how it's called, like.
No, but I'm asking a physical question. Where are the charges? If I just take the charges to be 0, where is the physics? It's a very simple question. What? They can cancel each other, but if I have 0 fields, Coulomb tells me that I have nothing, right? If the density is 0, then what are we solving? The answer is simple. On the boundaries of this, you are in the boundary. On the boundaries, there are charges. Without charges, there's something. So there will be on the boundary some charges. Without that, if there are no charges in the world, there's no electrostatics, there's no electromagnetism, and there's no discourse, right? So they will hide. So Laplace equation, when this is taken to 0, is defined. There are charges, but they are on some boundary conditions, and these are going to be important. And this is what I mentioned at the beginning of this class. You should read chapter 3 of Griffiths in order to be prepared, because the next step will be the Laplace equation. So now we'll go for 10 minutes break. I'm very happy there were no alarms. Yeah, I'll let you ask a question. And after that, I'll teach you maybe a new concept, maybe not, I don't know, about the energy of charging. How much energy do you need to invest to create a set of systems charge? And then there are some interesting things. So, yes, ask a question.
Like in a capacitor?
Yeah, I'm a professor, it's more general. It's just bringing charges together. It can be on any geometry. As a special case, it can include also the capacitor, but this is a very special case. I'll discuss, for example, what is the self-energy of an electron? Okay, you don't know what is the self-energy. Next lesson we'll explain it. What is the answer, even if you don't know what the self-energy of the electron? There is some interesting thing. The energy to make an electron is actually infinity, if its size is 0. We'll discuss this infinity and the different definitions of energy that create some problems, conceptual, that we will discuss. So to answer to you, it doesn't have to be a macroscopical body. It can be a simple 2 electrons together. It can be also a macroscopical body. We'll go from discrete to continuum, different descriptions. And we are trying to combine these two worlds, the macroscopical world and the microscopical world together. And this is all along the Griffiths book. For example, at the end of the book, he cares more about one charge moving in space. What is the electric and magnetic field? That's a very microscopical field, you can say, that leads you to particle physics and field theory. At the beginning, we'll do more macroscopic. For example, chapter 4 is electromagnetism in inside matter, polarization, which is more related to condensed matter. So there are many kind of connections here to many different systems. Okay, so let's have a break. Okay, so now we want to introduce some concept of energy. The energy is the following. We have some charges. Imagine we have charges at infinity, not all together separated at infinity, and let's say on the moon or whatever. And we want to bring them over here to the room. And then you'll have, eventually you will be left with a system which has some charges, positive, negative, whatever. This system has an energy inside it. It's part of the system. And this energy comes on the fact at the beginning there was, all the particles were far away, but then you had to invest work to bring them together. The question is very simple. What is this energy? How do we calculate it and how do we look at it? Maybe the most important thing is that we can calculate the energy of the system. How the most natural language at the beginning, things that you saw, I'm sure, is you lose the charges and you lose the distances between them, right? That's one way, and we will start from that. And this is, I think, in high school, you learn this. But then there will be a very different concept. That is, if I know the electric field, E, I can calculate the energy of the system. So the electric field itself in space, let's say I have some electric field here. I don't know exactly where the charge is. The electric field itself has some energy kind of built into it in some sense. So you can think about an energy density. So I have an electric field changing here in time, and I have a small volume here and a small volume there. You can say, roughly speaking, by the end of this lesson, that the energy here and there will be different because the fields here are different, and by how much, and things like that. This is super important later on in your studies if you continue, because this is related to second quantization, all kinds of how the photon is working. Because in quantum mechanics, for example, you always need Hamiltonians, right? Did you learn quantum mechanics? No? Okay. In quantum mechanics, in the Schrödinger equation, you did learn in the first year. So the Hamiltonian is important, right? This you know. And then the operator describing this Hamiltonian. So to define an operator, you need an energy. So the basic thing is the energy, not only from concept of conservation of energy and how much energy you need to do to build up something, but this energy, or the Hamiltonian, is in quantum mechanics related to dynamics through the Schrödinger equation. Well, like in classical mechanics also. So in short, the concept of energy is super important. That's all what I'm saying here. You don't need to go beyond that. So how do we start? So let us start with something very simple that you know, and then I'll pinpoint some difficulties or what I think are difficulties. So let's say I already fixed some set of charges. Let's say here I'm plotting discrete charges somewhere in space. And then I have a test charge, and I have a point A, and I have a point B. And the test charge, let's say, is Q. and I take this test charge from point A to point B. Then the question is very simple: how much work must I do? And you know this from, I think you know this. This is related to the potential difference between these 2 points, right? So, and why is that? Let me remind you of something very simple. Let us define. Now I'm going to use discrete charges. Discrete charges, you can think about them as point charges. Think about them as electrons, if you want, with 0 size. And this distinction later will become important when we go to continuum. It's a bit different in a continuum. Okay, so this work you do is, as usual, A to B FDL. This is, if you want, maybe the definition of work. But what is the... Okay, here I'm introducing in this class something new. What is this F? This is the electric field along the path that I have here, which is due to all the other charges here, and multiplied by Q, right? So what do I have here? This one is proportional to QE. It's QE, right? That's by definition the relation between force and charge, and force and electric field. And then I have EDL, an integral from A to B, but that is exactly the potential. And also you know that it doesn't matter what is the path I take, because the rotor of E is 0, I can take any path I want, the result will be the same. So this in short is Q VB minus VA. This is the amount of work that you do only moving these guys. But this is not the charge, this is not the energy of the system, right? The energy of the system, what is the system? Let's say this is the system. Or let's say this together with this is the system. We want to know how much it will cost us to build this system. That's the energy of the system. It's not this one. This is just this static and this thing. But from this law, you can immediately understand what is this system. Usually, okay, if I bring from infinity, if I bring Q from infinity, the word bring, if you can catch me, maybe it's a lie. If I bring Q from infinity, and I usually will have V infinity equals 0, that's just a notation. I say the potential at infinity, then this will be, let's say, Q VR. What do I mean by bring? I bring it to R, to point R. Okay, so that's good because here I have a potential difference, but if I set one of them to be 0, then it just becomes Q times VR. Okay, very simple. Why the word bring is a little bit problematic? Because we say all the time we are static. So if I bring, what does it mean bring? That if I move it, you know, this guy sees some current, right? So I'm lying. I like to lie, and all the books lie. So what do I mean by bring in actuality is, let's say, the way I think about it, let's bring them, but very, very slowly, adiabatically, and then you can forget about the time dependence of the bringing problem that will create all kinds of magnetic fields and things like that. But you can ask a legitimate question, you should ask ChatGPT, what happens if you bring them quickly? Will the final energy be what we say, yes or no? Independent of how fast we bring them. But that's a different story, we're not going, okay.
In that case, you need a sudden approximation.
Yeah, but the question is it true that it doesn't matter what is your speed, what is the energy? The answer should be, it doesn't depend, but it's not in the textbook, this proof. That's my point. Okay, so we should all go to the, I think you know where the place is? You know where the and yeah, we will come back, and it's unfortunate, but I insist to come back, and even if the lesson will be a bit more than, because we have to finish this no matter what. Okay, so yeah, let's go. Unless the missile will kill this Google Meet.
העבודה של כוח מגנטי הוא אפס, לא? אז זה אמור לא להשפיע.
כן, אוקיי, זה חלק מהתשובה. אבל יש גם, אם אתה מביא את זה מהר מספיק, אז יש אפקטים יחסיים. אז לא, כי שנה שעברה לא הייתי בהתחלה בארץ.
אז אנחנו מדבר על זה?
כן, חצי שני שנה. מה שהיה שנה שעברה, זה לא דיברו בהתחלה על יחסות של אלקטרומגנטיות. דיברו על יחסות פרטית באופן כללי. לא קשור לאלקטרומגנטיות. אנחנו נדבר בקורס הזה על יחסות פרטית של אלקטרומגנטיות. זה קיים בגריפיץ. אבל יש גם יחסות פרטית של מכניקה, שזה משהו אחר.
כן.
שכנראה לא אספיק את זה פה.
אוקיי, תודה.
כן, לקחתי ביום ראשון, אבל אז ראיתי שיש לא, סליחה, זה באופטיקה. באופטיקה גם יש לי תרגול בראשון ובראשון, אמרתי.
לא רואה להם. רגע, לא, שנייה. באופטיקה אני מדוטן?
באופטיקה אני מדוטן, אבל אני פשוט...
זה ביום...
תגיד לי, זה מה שאני צריך ממך, שתגיד לי מתי זה.
ביום...
נו. אני רוצה להזיז את זה. אבל גם תגיד לי באיזה חדר זה. תקן הכל בלוז. למה כתוב לי שזה יהודה? התרגול של יהודה הוא לא ביום ראשון מ-4 עד 5. לא באפליקציה של המדינה. וואו. מה יש לאייפון, האמת שזה יותר איטי מהחוויה שלי, אבל יותר איטי פשוט בגלל שכאילו כל המעברים וכל ההחלקות של המערכת ההפעלה של אפל לוקח רגע להתגדל לזה. אבל אתה מבין שעכשיו אתה נדפקת, כן? אתה עכשיו תהיה כל החיים עם
רגע, אני משנה.
זאת אומרת, עם שניהם. אין את השני אייפונים בעמדה, חול הנפש. כל אייפון בונה, עשה לך אינטרנצ'ה. לא משנה. לא אחרי. אני אומר על זאת. שנייה, פעם. תגיד לי מתי התרגול שלי. יום חמישי.
ברגע זה עדיין אין לנו, אבל אנחנו הולכים. היה רק התראה, התראה מראש.
התראה מקדימה.
התראה מקדימה.
בוא נלך. אוקיי. אני לא פה. אני לא פה, אני אומר לך.
אתה גם לא אמיתי, אתה רק בדמיון שלנו.
נכון מאוד.
עלה.
זה כבר לא
פשוט אתה תשמע אותו מגיע.
זה כאן.
תראו כמה
אתה
פעמים.
אמרת שהוא לא יכול לבוא להרצאה שלו, יש לך רק עוד אחד. איזה ככה חישובית זה חובה או בחירה? טוב, צריך להגיד לו שכאילו אפשר.
אתה רואה? אין אזעקה, אחי.
לא.
נו, זה
אמור
מערים
להיות.
אחרים. לא אמור להיות, אחי. אתה יכול לשמוע את זה גם מירושלים.
וואי, אתמול היה עירות, כאילו, שיכולתי לראות והייתי עם העיניים במחשב. האם קרה משהו או לא קרה?
אין אזעקה.
מה קרה?
להביא עוד קוף.
כן, זה משתנות שיש לי הרבה קוף. ששמנו את זה עכשיו בטלפון. שזה? אם קוף שזה והקשת הולכים כזו.
דריבוטר. של שדות אין מושג, אני יכול לבדוק. באיזה קורס כאילו, מתי שאני עושה את הרמון, יש לך משהו?
שדות.
אני אעשה את זה ב5.
איזה יהדות? ויכוח או הרצאה?
מ4 עד 6. האמת
שזה נראה כאילו אם זה היה נראה ממש חרא, אז הייתי עושה
כן, אני עם
גם
יהודה.
מרצה נחמד, מרצה עם כריזמה.
זהו, אני זוכר שפרה הלכתי להגיד שזה יהודה.
אני לא רוצה לוותר עליו.
שזה גם עושה.
כן, כן, זהו, אני...
יש לי מרצה
שאני גם עושה קוונטים.
אני באתי לעיניים, זה כמה אחד שנססות של
כולם בסדר בבית?
כנראה.
עכשיו ליד המקרר. אוקיי, אז עכשיו אנחנו... Okay, now we want to think about the energy of assembling the particle. That is, we bring them from far away, they are discrete. The beginning, they are far away one from another, so there's no energy, no electrostatic energy. And then we bring them together and then you pay a price because you need to work against forces, etc. The question is, what is this total energy of the discrete system? Total energy or work you need to put in of a discrete system. So the claim is, and I'll soon show it, and possibly you know this, this is 1/2 sum over the Qi VRI. So I'm thinking about a system of charges. There's Q1, there's Q2, there's Q3, and there's Q4. And this is the final state. And at the beginning, they were all separately at infinity. I brought them together, and now this is the work I needed to do, and that means this is the energy of the system. Somehow I can use this energy, maybe I can let them go away and I can use it in some option. But this is the energy of the system. And what is Qi? These are the charges. What is VR? Here there's a little subtlety. It's the potential created by all the other charges. So of course you don't include in this V the potential that, let's say we're looking at particle 4. So this is I equal 1 till n. In our example, n is equal 4. So when you say VRI, it is the potential excluding the self-interaction without it. So this one is excluding self-interaction. So VRI is the potential due to all charges except particle I. Now, this equation, this is very simple to say, but to prove. So let us look at n equal 2, and we start a system like this. So the two particles are far away, I don't plot them. The energy here is 0. Now I bring one of them. First I bring one of them from infinity, and it's at point R1. How much energy do I need to spend here? Nothing, because there's nothing to act upon. And then I bring this, so this is stage, let's call it stage 0, stage 1. And then I say, okay, then I have two particles, Q1 and Q2. Now, when I bought the second particle, it cost me some work, and let us look what it is. So first let us use the equation simply. Discrete. So this is simply half. This is this half that I claim that you need to have here. Q1 VR1 plus half Q2 VR2. This is what we claim. But this is easy to calculate. 1 Q1 Q2 4 pi epsilon 0 R12. R12 is the distance between particle 1 and 2. That is this distance, right? Because this is the potential that particle 2 is creating on point R1, and then you have exactly the same Q1, Q2, 4 pi epsilon 0, R12, and this is of course equal Q1, Q2, 4 pi epsilon 0, R12. And this is the correct answer from this diagram. I hope you all see, because you just bring particle. It doesn't matter what is the path, again, because the rotor is 0. You bring it here, and then what you actually care is the potential of this guy on here, and this is exactly the answer that you get. So I added it twice. So the trick here, in this process, I have to only look at this part, only what is the potential here. When I do this solution, I need to add this half, and then things cancel. Now you can easily prove this for more and more particles, but this equation is very general. So this is the answer. This is the simple answer. You need to know the potential, and you need to know the charges. Sometimes you know the charges, and sometimes you know the potential. For example, in this trivial problem, and sometimes you don't know both of them. So maybe we would like to reduce the variables. Here I have n charges and the potential where they are located. Maybe we can use some other physical quantity, which eventually becomes important. And what is that physical quantity? It's going to be eventually the electric field itself. So this is one way to present this result, but it's not the unique way and not necessarily the best way. Okay, so now I want to consider actually continuum, or if you go to Griffiths, he will give you a continuum description. Now, the continuum, in the continuum you have, if you want to think about the density, what is the density of the final set of particles? Like here, it's a sum of two delta functions, right? So I can do an integration, and with delta functions I can get this result. That's what you would expect, right? More or less, if you understand what I'm saying. So what, this is continuum. What do I mean by continuum? Let's think about it in two ways. One of them is that the charges are smeared. There's some field rho of R that gives you the charge density, but it's not necessarily density. But if you insist, it's also the delta functions, sum of delta functions. So just, I'm going to complicate this a bit, but one way to look at the charge density is sum over R minus Ri Qi. And if you, this E, eventually it will be an electric field, sooner you will see. This I'm going to write as V. What is V? This is the potential. D tau. Now, these two equations look the same, right? But they are not, actually. There's a small difference. I cheated a little bit. They are the same if I put here a delta function, right? Then I'll get a sum. Then this potential will turn into this potential. Is this correct? No, because that potential is the whole potential, just the potential, not excluding particles, etc. So it's a bit different. This potential is just the potential without this exclusion of single particles. So what's going on here? Okay, but let us start with this definition and see what happens and discuss, and eventually I'll even prove this, but let us see what this means. First of all, what is rho in general? It's epsilon 0. This is Gauss law. So this is good because I can replace this rho with this electric field, and the potential also is related to the electric field. So we have already two electric fields hiding in one equation. So this is a good move in my opinion. And then I can write WE, the assembly of these things, is 1/2 epsilon 0. Okay, this is the volume. Now, okay, here there's also an issue. I can integrate this over all space or over the space where rho is not equal to 0. But it's the same thing. Why? Because if the density is 0 somewhere, I can integrate there. I can integrate till infinity if I want, because the density is going to be 0 in many places. So it's okay to integrate more than what you should, based on the locations of the density. So here rho is equal to 0. This is the configuration I think about. It doesn't have to be in one pocket. It can have many disconnected things. This is not important. So the volume can be stretched till infinity. And then if I plug this in here, then I have rho E times, how do I want to, V d tau. V is again the potential. And this is still on the volume. This is not an infinite integral on some volume where the density is. This shape I'm integrating over, like I had at the beginning, okay? So now I can change this till infinity. Okay, I'll take this to infinity. Or to be something very big, to be more correct. And then this is equal, okay, here I have simply, this is like that. Here I can do something called integration by parts. Why is this useful? I have this divergence on E, I want to put it on V. And then what will I get? I'll get the E. Yeah. So I do this and integration by part, then I have E0 over 2. I have two terms. One is E grad V d tau, and one is a boundary term. So this is a little bit different than what you are used to in usual integration by parts, because these are functions in 3 dimensions. So the final, this is the boundary term. If you remember, if you have usual integration by parts in 1 dimension, you have the two functions multiplied by each other. Here you don't have the two functions multiplied by each other, but here you have the function not on the boundary, which is x1 and x2 in the usual integration by part, but the integral over all the surface of the volume. Now, as I mentioned before, I can take the volume to be large. So let's say here I have many charges, and I'm taking it now to be very large, over all space essentially, taken to the infinity. The integration is going to be over here. This is allowed because what I said before. What will happen to this guy? Let's say this is a charge system. The total charge is something far away.
0.
Well, it goes to 0, that is correct, but you need to be a little bit more careful because dA also depends on R. Because
And it goes to infinity.
dA, I have here a surface, think about it as a sphere. dA is proportional to R squared. So this guy is proportional to R squared, the surface, the size of the sphere that I put around everything. What is the potential? It's 1 over R. This one is 1 over R squared. The point is that all this goes to 0 together like 1 over R. So maybe you meant that all this integral goes to 0, that is
0, not infinity.
at infinity it goes to 0,
Yeah.
right, sorry. My mistake. I was kidding now. So it goes to 0, and it goes to 0 like 1 over R at large distances, and then I can forget about this one. Provided that I integrate over all space, not only of the where the charges are, I have to integrate till far away. So now I have here integration till all space, over all space. dV is the electric field. And then I get this important equation that the electric, which is different, looks different, but it's the same thing, or more or less the same thing. What is the energy, if you want, of a charge system in electrostatics? It's very simple. It's the integral all space, that is stretching till infinity. You need to know the electric field here, there, everywhere. If you don't know this electric field, you cannot calculate the energy. E squared d tau. And this is what I mentioned before, that if I have here this room, and I have some electric field here, this doesn't give you the energy of the whole charge system, but it gives you the density of the energy at this position in space. So I have many, E squared is like the density of the energy in space. And this is an important equation for two reasons. One of them is that you'll use it a lot, and then when you quantize things, you actually quantize this object, but that's in second degree. But more importantly, imagine now we started with this system, right? Now, here what you're saying is, okay, here there is a price you pay. I need to know the electric field everywhere. But if you can measure the electric field everywhere, you don't need to know the exact positions of the charges. It's not that one is better than the other. Both of them are good. Some cases you would like to know, use this one. In some cases you use the other one. Both of them are the same from point of view of calculations. But now there is some problems. What exactly is this energy? Does it really make sense? So what is the problem here? Related to the small cheat I had here. What is the energy of a point charge now? I can take here a delta function on the origin, and I can calculate this. what will I get? Yeah, I'll get infinity. So if I have a point charge modeled by a delta function density, I get infinity. And this is very easy to show. And we want to discuss this. What does this mean?
But it makes sense if we're claiming that it's infinitesimal point.
Right.
If
Yeah,
the size of the
That's a good answer. That's one of the answers. So there are two aspects here. One is, let's say I have a theory and I get infinity. Now the question is, what do I do with the theory? Because if the answer is infinity, how can I go to, if I go to buy some ice cream in the shop, but I give the guy infinity amount of money, he cannot give me change. So it's not a useful concept in that sense. That's one answer. But the other thing is, as you point out, and we will talk about this, we are using point charges, and point charges have infinite amount of energy embedded in them. So you can think about the electron as if it is, now it becomes a little bit philosophical, what is the size of an electron? So we believe it is of zero charge, or we treat it as zero charge, but we are not sure. The actual charge, the size of the electron, if I remember correctly, is, we don't know what it is, but there is a bound. The bound is 10 to the minus 17 meters. It's something smaller than that, but we don't know exactly. But if it's zero, then the energy is infinity. So, but let's go back just to the simple thing. Let's just use this equation. Point charge. Then we just need to integrate the electric field, just so it will be in your notebook. So the W, this is what is called self-energy of the electron. You integrate over all space, as I mentioned. You have here this epsilon 0, then you have 4 pi epsilon 0 squared from the Coulomb law. And then you have here Q, the charge of the electron, R squared. This will be to the power 4, right? Because I have E to the power 2, 1 over R to power 4. And then I'll have all this R squared dr d cosine theta d phi. Let us write it explicitly. 0 to 2 pi, 0 to infinity, minus 1 to 1. Usual big sphere that I'm using. And then you immediately see that the integral over R is 1 over R squared, the integral from 0 to infinity. This gives you infinity, right? Because the integral is 1 over R, and if you put 1 over 0, that gives you infinity. There are subtle points that for certain values, if you put here some general exponent, the divergence can come from infinity actually. But that's a different story. For 2, it comes from 0. So what you said is correctly, the divergence comes from small scales, because exactly what you said, we are assuming that the size of this object is 0, and so this is infinity. Now, let us go one step beyond this. What is the energy? So this is not useful in some sense, but it's, as he mentions, it's not the end of the world, because maybe it's actually true. Maybe if you have a charge Q on 0 space, someone needs to compress it. It will cost you infinity. God can do everything, so okay, you can also do that, maybe. So let us go to something more, from my point of view at least, more informative, to relate between this equation and what we had before. Remember, before it was very simple. It was high school, right? It was simple formula. In the university, we make things complicated with no need, sometimes say, but I think there is some need to talk about these problems. So anyway, so what we could do as an exercise, I'll not do it, but this is not in Mr. Griffith's book. It's in a great book, which is way more complicated, called Jackson. electrodynamics. This is like old book. So let us assume we have 2 point charges, 1 and 2. And then the total electric field, again, these create Coulomb fields. We know exactly what are the fields, so we know the field in all space, right? This creates 2 fields from the superposition principle. This is E1 and E2. And I can write it down. I'm not going to write it down because this is just Coulomb fields. What is the total field? It's the integral over all space of the sum. What is the sum? It's E1 squared plus E2 squared plus 2 E1 E2 d tau, and I need to multiply this by epsilon 0 over 2. Now, what happens? What is this integral and this integral? It's exactly like before, I claim. I think it's intuitive, I'm not proving, but it's exactly the same, because what I just write down, I just take the 1 over r squared potential integrate. It is shifted because it's on some point in space, but it's not important because you go close to this point, it will diverge in the same way. So this guy is, what is this guy? This is infinity plus infinity from these 2 terms.
The second term is 1 multiplied by 2 multiplied by 1, or
1
the index
squared, this was my joke, this is squared. This is these 2 guys are the same, but
Okay.
the positions are R1 and R2, but the divergence is the same, and it will give you the same because they are
They're the
just
same.
coulombs.
They're the same because we're integrating all space.
Yeah, you just have a field. Imagine a field that at a point R1 or a point R2 goes like 1 over R minus R1, it diverges, and then the position of this in the integration is not important because you're integrating over all space, so you can shift the R1 and R2. Or in the previous problem, I defined this as 0, but it is totally irrelevant to anything. So we are left with this integral. Now this integral, I can write down the Coulomb field of E1, a Coulomb field of E2. It will depend on the 2 positions, R1 and R2, right? Then you need to integrate. As physicists, maybe some of you can guess the answer. What do you expect the answer? You can also do the integral, ask Chad to go to Jackson. What is the answer? If you do this integral, you do this integral with the cosine theorem or the sine theorem, I don't remember. But let's call this energy from these 2 guys W12. This energy W12 is very simple. Simply Q1, Q2, 4 pi, epsilon 0, R1 minus R2. I'm not proving this, but I'm telling you. Because from physicists' point of view, this is nearly obvious. What is this? This is what I told you before, was the charging of 2 charges that come. You bring one, no work against vacuum. You bring the second. It is exactly the same thing. So this formula is exactly what I had at the beginning, shifted by 2 times infinity. In physics, we don't care about this infinity, or we do care, his point of view. Okay, there are 2 philosophies. We do care. One group of people will say, oh, but the radius of the electron is not exactly 0. Let us solve that problem soon. Another thing is, we don't care about the energy, but energy differences. That is, when we brought the 2 charges from infinity, they already had this infinity inside them. And what you actually do the work is only this part. So the fact that there was infinity is not so important. And this is just a reformulation of something that you know, that what you really care is the energy differences between two states. You don't care, you can call it plus infinity, you don't care about it. It's not that you need to go back home and worry too much about this infinity. It's not so bad. You can live with it. But when you read the books, they put it under the rug, and I thought it is a little bit interesting. So, okay, Jackson, and again, you can do this integral you can show this, so everything is okay from an operational point of view, and you understand a little bit what is the meaning of the discrete energy. So now we can, so now we are left with two things. One of them, okay, let's assume that the electron is not a point particle. What is the energy of an electron? Let us assume that this, now we need a model. And I have no idea what is an electron because it's too small and no one knows what exactly is an electron. But as a very rough approximation, let us assume the electron is a sphere from symmetry, and on the sphere we have some charge. What is the charge on the sphere? The electric charge of the one electron. And then we have a finite radius. We always can take the radius to be 0, and then we will see what happens. Let's see the energy of this object. We have these objects. It doesn't have to be an electron. It's just the energy of a spherical object with charge uniformly distributed on its surface. So this is a physical question. It doesn't have to be microscopic. It can be a macroscopic object, but let's see what happens. So now the sphere, radius r, 0 with uniform charge, total charge is Q. So the whole trick is very simple. What is the field? The field, so we have this, this is in high school. You have this problem in high school, but I don't think they solved the energy of this problem. You have this object, right? You have the charge uniformly distributed. What is, for R less than R0, what is the electric field? 0. Every time I ask you a question, answer 0 or infinity, 50% you'll be correct. So this is 0. This is known from the Gauss law that you learn in high school. You put here a Gauss surface and there's no charge enclosed, and then immediately this is 0. And what is it outside? It's also trivial. It's also from the Gauss integral form. It's like the charge was inside the middle. So this is a trivial problem. So this is simply like the Coulomb. Right? This is just the Coulomb force, as if all the charge here is in the middle. Now I introduces this cutoff radius, R0. Now I'm gonna just put it here inside here and do this integration. Now the integral will not diverge, unlike what we had before. So what we have here WE. So I need to measure the electric field everywhere. Inside is 0, I can measure it or not measure it. And then this is equal to the following. I just use this equation. It's epsilon 0 over 2, 4 pi epsilon 0 squared, Q squared. Integral, okay, there are several integrals. dr, r squared. Again, I need to integrate over all space. I wrote it here.
Are you integrating from R0 now?
Well, okay, I'll integrate from R0 to infinity because I'm using here the fact that E0 below that, this is the main issue, d cosine theta d phi 0 to 2 pi minus 1 to 1, and here I have 1 over r to the power 4. Did I miss something? No, I don't think so. So here I have r squared, 1 over r. So when I integrate, what will I get? 1 over r0. Okay, because integral from r0 to the infinity over r2 dr, this gives you 1 over r0. which is also obvious from units point of view because the units here are trivial. So WE, if I do this integral, is, okay, this is 16, you have here, okay, this guy here gives you 4 pi. So here I have 4 squared, 1 4 will go, and then you have 4 times 2, this will be 8, but you can trust me in this, you have epsilon 0 down here. We have here 8 pi q squared 1 over r0. And this was obvious, these units are obvious from the beginning because these are the units of energy. You have only one length scale in the problem, so these are the correct energy units. Remember that the potential is q over r0 times this epsilon, and then the energy unit you need to multiply by q. That's why you have q squared as usual. And what does this say? Let's take r0 to 0. Then WE, as we said before, goes to infinity. But if it's finite, it's finite. You can put in the number, this upper bound I mentioned, 10 to the minus 17 meters. You can put it here for the electron. You can put here the charge of the electron. And then you can get some energy. Now the question is, so what? First of all, it's a bound. And to what energy to compare it to? So, as a wild guess, what would you compare it to what other energy of the electron you have? In what sense, let's say this number is 10 to the minus 17. Let's say this is the size of the electron. Let's say, what are the other scale of energy of an electron? It's simply mc squared. mc squared. That's, you would say the charging energy is also the mass of the guy if you want, or you want to compare one energy to another. If you put here 10 to the minus 17, you get an energy which is much, much bigger than mc squared. It's much, much bigger than the relativistic rest energy. So it's not related to that for sure. This energy with this number is much bigger. But again, we don't know what is R0 for an electron. We know that there's an upper bound, but that's it. We don't know what it is, and that is fine. So if I did all these type of exercises, and if I would put this these two charges very far away from R0, then to a very good approximation, these two numbers, infinity and infinity, would be replaced, assuming that the two charges are the same, by this number, which is finite. So I can solve the problem of infinity in this way. Say, okay, there's some lower cutoff, I do the integrations, and now there's no lower cutoff. So sometimes the math gives you kind of nonsense infinities, but you don't need to worry, and you need to think why. Sometimes it's saying something very bad with the theory is happening. Sometimes it means that you pushed the theory too much and you got out a result which is a bit crazy. So now I still owe you something because I want to give you, what is the time? Oh yeah, there is the time. So very briefly, I had a problem with this main equation that we started because I said it's rho v integration over all space. So we can kind of a little bit improve the proof. We didn't prove that equation because we used just the potential, not everything. So there is a way to do that, which is again not in Griffiths. I found it in chat actually. Chat can teach you everything if you know how to ask questions. So the only reason to read books and come to lessons is to know how to ask questions. And ask your friends questions, because that's the only valuable thing left. Everything else is, at least my questions, maybe if you can ask. I'm not, okay, I'll put it differently. Chat is very good in some things and very bad at other things. But in electrodynamics, it's very, very good. And the reason is very obvious, because there are so many courses, so it can learn for itself from all the universities all over the world, and it's really unbelievable. If you go to other specialized courses, it's not true. The second degree courses that the amount of information is not so much available. But in electrodynamics, at least my equation, maybe I'm asking stupid questions, I mean, questions that can go to a class, that's what I mean. Okay, so you should use it, so I asked, let us look at a different way of this charging process. You remember, I started with one charge, right? There was one discrete charge, I bought one charge, then I bought the other. But I don't want to work with discrete because I had a problem between discrete and continuous. So let us start building up charges, but in a continuous way. So I have a field density everywhere, and I bring in fields. So the idea is I will define rho of lambda as lambda rho of r. Let me explain. Lambda is a parameter that goes between 1 and 0. The final density that you have at the end of the day is rho of r. I'm bringing many charges, and then eventually I have rho of r. At the beginning I had nothing, right? So the 0 reflects at the beginning I had nothing, and 1 reflects at the end I had rho of r, whatever it is. And I go between them. So in a picturesque way, you can think of it as a time process, and there was one comment by, it has to be adiabatic in principle. This even Chat says adiabatic, but he said, okay, but if I create magnetic fields, they don't do work. That was a very good comment he made. However, the electric fields of relativistic particles are a bit different. It's a bit more complicated, so we will leave that question for Chat. No, for the end of the course or things like that. I'm not sure, I'll come back to it. But anyway, we are using now this adiabatic thing that we are bringing very slowly, these charges slowly one after the other. So you can think about this lambda as a function of time. So this is a lambda equals 0 is like time equals 0, and then I have simply nothing. And then let's say at some other time, let's say you go to lambda half, then okay, I have some charge density, but it's kind of like that. And then lambda equal 1 at the end, I just make more points. I think you understand my point. You are increasing the density, but uniformly. I mean, you can ask many questions of Chat. You can ask, okay, but if I don't want to do it like that, I change this part here and then that part there, things like that. You can. This is the nice thing about Chat. You can immediately extend the dialogue you have with them. It's nearly as good as students. No, it's much better because you can ask all kinds of questions and see what comes out, or you can start thinking about it by yourself. Anyway, hopefully this process of time 0, some middle time, is clear when you are bringing the charges from infinity. So one key point is what is the potential at point r as a function of lambda. And the key point to understand it, it's trivial from the Gauss law, is that this is proportional to lambda times VR. What is VR? VR is the potential that you have at the end. And what is here? The potential is 0, and here it will be lambda equal half times the final potential. Why do I say this? Because what is the Gauss law? div E equal rho. Now, rho multiplied by lambda. So the E is multiplied by lambda. You see what I mean, I think, when you go through. So the reason in short is that the equations are linear. If they would be non-linear, that would be wrong, but the basic Gauss law is linear. So, okay, this is the potential, and then it goes, during the process of building, it goes into this, it changes gradually. Now we want to ask, what is delta rho? What is delta rho is that in one small time step, I bring in some small density proportional to it is related to the rho of r, but I bring in one charge before. Now I'm bringing some density field. With this is called delta rho. But what is delta rho? 1 second.
5 minutes.
What?
We have another class in 5 minutes. So.
Yeah, but there was an alarm, so you can. I'm sorry, but you can. You can listen to me later. That's the wonder thing. I think it's recorded. So I'll continue because we did miss time. I apologize for that. Anyway, I'm so excited. So, okay, so we have this delta rho. And you can also find it on chat, so you can ask chat to do this. I have this delta rho times this delta lambda. And then I need to think, what is delta W? That is the energy that I add by bringing one layer, small delta layer of densities. That layer is the potential that we had already. This is okay. This is without the new part. V of lambda multiplied by delta P, delta tau over the space where you have densities. Because again, this thing is simply this is this delta P is here, this is this delta P here. I didn't use yet lambda. Now I want to integrate. What is the total energy? I want to integrate the initial state to the final state. Now I do that with the lambda. I integrate over lambda. That is from 0 to 1 d lambda. I use the fact that this is proportional to lambda here. So I have here lambda. And then I have integration, this delta rho is this rho, delta tau, v all space. And the whole beauty of this, and the beauty or whatever you want to call it, or triviality, what is this integral? D lambda lambda from 0 to 1, that is this half. And this is what this is the formula that I gave you before, so we get what we had before. From here we started actually, half rho v d tau. Now, this adiabatic motion was a linear adiabatic. Then you can say, well, why do you do a linear? Let's do a nonlinear function. You'll get exactly the same thing. This I invented this after chat gave me the answer like this. I said, okay, you can ask something small. So if you have here a function f of lambda that goes from 0 to 1 somehow, doesn't matter how, then what you will get here is d lambda f tag of lambda f, and that will give you half, no matter what is this function. So this is a more general proof that no matter how you scale f of lambda, it has to start at 0 and it has to go to 1. At some lambda critical after some time which corresponding to this parameter. No matter what is this function, you'll always get this half. So this is a kind of general proof that you can not find, as far as I know, in textbook, or some way to think about it. That, you know, if you read the book, you go to chat, you can ask these type of questions yourself.